Hi everyone, this is Dr. Hopkins with your next in the series of videos that we're going to use for Chemistry 472. And this is our second video on gases. And so we ended the last video talking about the ideal gas equation. Every first year student knows the ideal gas equation, but what we're going to do is look at this through the lens of a physical chemist, right? So a physical chemist, one of the goals are to develop theories, and models that can predict new behaviors or explain old behaviors or do both. Okay, and so this equation of state describes behavior of what we consider to be an ideal gas. Now clearly we have to come up with some assumptions to develop a model to describe gases, and we're describing all gases with a very simple equation. So our assumptions that we're using are basically listed in bullet points here. So we have the gas particles move randomly, so there's no reason that they should move one direction over another. Just whatever directions they're going, they kind of tend to move until they hit something and bounce the other direction or whatever, another direction. So they move randomly throughout the container, right? So they don't congregate in one spot, congregate in another spot, and they have a speed or an average speed, kinetic energy, proportional to temperature. So higher temperature, faster on average particles. Lower temperature, slower on average particles. So that's just the average. Clearly, you can have some subset of the population that's stopped, some subset of the population that's going much faster, and so forth. And then the second bullet point, collisions are elastic. This is a concept from physics. We're not really going to delve into this. Basically, it means that the energy in a collision is conserved. And then the last two are the ones we're going to deal with a little bit more in detail. And then we're going to assume that the volume of the gas is actually small or negligible compared to the volume of the container. Okay, so it means that the gas particles are free to move throughout the entire volume of the container because they don't get stopped by other gas particles. Okay, and then the last one is that there are no intermolecular interactions between particles. All right. So let's look at the last two assumptions, because the one thing you want to do when you develop a model is you want to look at and see, are the assumptions you're making valid, or maybe a better question is, are they valid under certain conditions, right? And if they're not valid on those conditions, you need to revise your model. All right, so let's look at the one about gas volume is negligible. So here we have a couple of crudely drawn pictures that I have showing if we have a gas and we were to just collect it all into one part of the volume, you can see in this first frame, it occupies a very small compared to the rest. So pretty much there's almost no volume occupied by the gas. And so if we let them now spread out, according to our first assumption that they're freely throughout the container and moving, you can see that pretty much any of these particles can move any direction they want, almost any direction they want, without hitting a particle. So they're going to hit another part of the wall. So that's kind of the basis behind this, is that if we have a gas that is, if we have a low enough number of gas particles, then the container volume is very large compared to the volume of the gases. So this assumption is good when we have low pressure, high volumes, and low number of gas particles, or N, moles. And then the last assumption was that there are no intermolecular interactions. Okay, so this is something that I always say is not something we really want to do as a chemist, right? As chemists, we've been learning that the molecules matter, that structure matters, that intermolecular forces matter. But if you think about it, if we have just a few gas particles around, so in this second here, we have just a few around, they're not really close enough to interact. So they're just moving around in mostly empty space throughout the volume of the container, right? So there's a distance dependence to intermolecular forces, and they're not really falling within the distance. And the other thing is that when they do actually get within a distance that the intermolecular force can interact, or the two particles, atoms, molecules can interact, we're going to assume if a case is that they're going high enough speed, remember the temperature, then they pretty much have enough kinetic energy to overcome any of these intermolecular interactions. So this assumption is once again good when we have pretty much low pressure, high volume, actually really higher temperature, and low number of moles. So those assumptions are good under those conditions. All right, so that allows us to then state the Dalton's law of partial pressure. This is kind of a sidebar here, which is basically that the total pressure of a mixture of gases. Now, this is where we go back and say, hey, the intermolecular forces are not important. If intermolecular forces aren't important, then the actual identity of the gases is important. It only depends on the total moles of gas. So the total moles of gas doesn't matter. It doesn't matter whether oxygen, nitrogen, or hexanes. It's just total moles because we're not really factoring in structure. And so the total pressure is the sum of the partial pressures. The partial pressure of any component is just the mole fraction. So whatever fraction of the total moles it is of that component times the total pressure. So that's Dalton's law. And we'll use that throughout. And then, so we have examples of the ideal gas. We had examples where the ideal gas holds and what it allows us to do. It then allows us the mixtures of gases we can just treat as if they're all one gas. It doesn't really matter. That's Dalton's law. So under what conditions will these properties not match the ideal gas equation? So at what point do we not use the ideal gas equation? And you'll notice in every case we said low pressure, high volume. So if we put our gas, or we put enough gas in, so large numbers of moles, high pressures, into small containers, then what happens? Well, then we have enough gas particles around to deviate from ideality. Okay, so we're going to make a measurement of that, and then we're going to introduce this measure of ideality. It's this compression factor. And basically what we've taken is the ideal gas equation, and we've divided it out where it should be if it were ideal 1. So PV, so pressure, we have R, we have temperature, so Z is our compression factor. VM is kind of new, but it's a molar volume. It basically gets rid of any kind of additional moles. So it's just volume divided by the number of moles. And so for an ideal gas, all pressure, volume, temperature, Z equals 1. All right, so basically what it means is there's no repulsion, there's no attraction. We've suppressed any intermolecular forces. Now, in some cases, we're going to get non-ideal behavior. And so if this Z is greater than 1, right? So if this is larger than what this should be, that means that the pressure or the kind of molar volume, so that the gas wants to occupy, is larger than what it would be in ideality. So that means that these gases are repelling each other. They're making their volume larger than it should be if it were an ideal gas. So for greater than 1, repulsive forces are dominating, and likewise less than 1, right? So that means then the numerator on this expression is smaller than what you would expect for an ideal gas, and is less than 1, the attractive forces are dominant. So it's pulling it, it's making the volume smaller than it would be if it were ideal. And so what you can do is you can go through and plot these compressibility factor versus P plots, and you have one in 7.5, and it'll show where gases deviate from ideality. So you can see where the gases are close to 1, we can pretty much treat it as an ideal gas. But as you increase the pressure or change the pressure, this Z may actually go above or below 1, then you have deviation from ideality. And actually, for the same gas, you change the pressure, you can switch it from repulsive to attractive forces dominating. So it doesn't really matter in that case. And so that's deviations to ideal gas. So what we're going to do in the next video is talk about real gases. So how can we treat then how can we make an equation to explain the properties of a real gas?